Welcome. Today we begin Chapter 6, Probability, and this is Section 6.1, Introduction to Probability. We look at basic ideas and complementary events. Let's start off with an example. Suppose there is an experiment where you toss a coin 4 times and you record H or T for the result of the coin. You can get 16 possible outcomes. Let's call this our sample space, the set of all possible outcomes. Now, you might be particularly interested in one event, an event where exactly 2 of the flips are heads. So that is a subset, really, of the sample space. So what is the probability that this event occurs? I denote it PR of E, the probability that event E occurs. And so that is 6 out of 16. So the size of the event divided by the size of the sample space, which reduces to 3/8. In general, we say an experiment is conducted with a sample space S of equally likely outcomes. An event is a subset E that's a subset of S. And the probability that E occurs is, the probability of E is the number of elements of E divided by the number of elements in S. You try. What is the probability that in 10 tosses of a fair coin, exactly 5 of the outcomes will be heads? Pause the video, give this a try, and then start up again to check your work. Let's take a look. We have 10 tosses of a fair coin. What is the sample space? All those possible outcomes, which is 2 to the 10th. You can imagine 10 blanks, and each blank has to be filled with H or T, so 2 to the 10. That's the size of our sample space. But what is the event? The event is that exactly 5 of the outcomes are heads. Exactly 5. So take 10 of those blanks and choose which 5 are heads. 10 choose 5. And so we have the size of the event divided by the size of the sample space, and we get a number that's about 1/4. Here's another example. You roll a pair of dice. What is the probability that the sum is a multiple of 4? So there are 11 possible sums. There they are, 2 through 12, 11 possible sums, and 3 of these are multiples of 4. So we think the answer is 3/11. But no, you would be so wrong if that's what you thought. There is a problem. What is the problem with this calculation? If you need to pause the video and think about it for a second, do that. But then, okay, the trouble is that these different sums are not equally likely to occur. In fact, the 8 as a sum is much more likely to happen than the 12. The 12, there's only one way to get that. Both of the dice have to be 6. Whereas with the 8, you could have a 2 and a 6, or a 3 and a 5, or a 4 and a 4. So this is something to watch out for. If our results are not equally likely, then they can't work as a sample space. But let's take this problem and think about it in a different way. Maybe I'll put the results of die 1 on the left and the results of die 2 across the top. Now I have 36 possibilities, and these 36 possibilities are equally likely. And now I can just check off the boxes for all of those outcomes that give a result where the sum is a multiple of 4. So 36 possible equally likely outcomes, and I see that 9 of those give me a sum of 4. So there we have it. Our probability that the sum is 4 is actually 0.25. A lot of problems in this section deal with probability with cards. Now, a standard deck of playing cards has 52 cards, and they're broken up into 4 suits. The 4 suits are hearts, diamonds, spades, and clubs. And each suit has 13 different ranks, ace up through king. A lot of times when we work with cards, it can be useful to visualize a display like this with all the suits and all the ranks laid out. In poker, for example, it often happens that you have a 5-card hand. So 5 cards are just randomly given to you, and the order of those cards doesn't matter. We figure out the number of 5-card hands by simply taking 52, choose 5. I have 52 cards here. 1, 2, 3, 4, 5. There we go. I've randomly chosen 5. How many ways could I have done that? 52 choose 5, which is about 2.6 million. You try. All right, take a look at these problems and think about them for a little bit. Pause the video and then start up again when you are ready to check your work. All right, let's take a look. What is the probability that a hand of 5 cards from a standard deck of cards will be all spades? So I know that the denominator is going to be 52 choose 5. That's how many ways I can choose a hand of 5 cards. But the 13 is because there are 13 spades, and so I'm choosing 5 out of my 13 spades. In the next question, what's the probability that this hand of 5 cards is a flush? In other words, 5 cards of the same suit. So in this case, there are 4 different suits, so it's like I choose the suit, and then once I have the suit selected, I need to choose the 5 cards within that suit. So 4 times 13 choose 5. And then of course that's divided by 52 choose 5. And then the last question, how many of these 5-card hands will consist of 4 of a kind? Perhaps I should have said this before I stopped the video. 4 of a kind means 4 cards of the same rank, and then a 5th additional card that's anything else. So we figure this out by saying 13 times 48. Now where did that 13 times 48 come from? The 13, that's how many ways you can choose 4 cards of the same rank. But then you have 1 card left over, and so there are 48 ways to choose that one other card. So 13 times 48 is the number of ways that I can choose 4 of a kind. Let's talk about big idea number 2, complementary events. And this is simple but exceedingly useful. This idea that the probability that something happens is 1 minus the probability that it doesn't happen. We might represent this symbolically by saying the probability of an event equals 1 minus the probability of not the event. So sometimes you see the bar over the E, meaning the event doesn't occur. We can also solve for the probability that something doesn't happen. We can say the probability that event E does not occur is 1 minus the probability that E does occur. Here's an example. What is the probability that when a die is rolled 3 times, some number is repeated? So what is the opposite of that event? Some number is repeated. If that doesn't happen, then there are no repeats, right? The opposite of some number being repeated is that there are no repeats. So let's figure out 1 minus the probability that there are no repeats. The probability that there are no repeats ends up being 6 permute 3 over 6 cubed. 6 times 5 times 4. You can imagine that. Essentially, there are 3 blanks to fill for these 3 rolls of the die. And the first outcome can be anything. There are 6 ways to fill that blank. But then after that, you can't be the same number as the first. So there's 5 ways to fill that second blank. And then there are 4 ways to fill that third blank. So 6 times 5 times 4. That's what goes in the numerator. And then in the denominator, the total number of ways of having an outcome with 3 rolls of a die. And then the result is 5/9. So that's the probability that there are no repeats. Then to answer our question, we take 1 minus the 5/9 to get our result. So 4/9. 4/9 is the probability that some number is repeated. You try. Take a look at these 2 questions. Think about them for a little bit. Pause the video to work out your answer, and then when you are ready to check your work, start it up again. All right, let's see here. So first one, what's the probability that when a standard die is rolled 10 times in a row, at least one of the rolls is a 6? This at least one occurs so often that should trigger something. When you see at least one, think of using the complement event, because the opposite of at least one, if that doesn't occur, then the answer is none. It never occurs. So I really want to compute 1 minus the probability that there are no 6s. So the probability that there are no 6s means that every time I roll, I get something other than a 6. So 5 possibilities, 5 to the 10th, divided by all the possibilities, 6 to the 10. So 1 minus 5 to the 10 over 6 to the 10 ends up being about 0.8385. So a little bit more than 83%. The second question, in a class of 25 students, each student writes down a random 2-digit number, 10 to 99, so there are 90 of those numbers. What is the probability that 2 people write down the same number? So this is the section on complementary events, right? So you're thinking, well, what is the complement of 2 people writing the same number? I guess it would be that everybody writes down distinct numbers, right? So let's do 1 minus the probability that everyone writes down distinct numbers. And so if they all write down distinct numbers, it's kind of like the die problem on the previous slide. There's 90 ways the first person can write down a number, and then there's 89 ways the next person can write a number, and then 88 ways the person after that, all the way down until you get 25 factors. And then, so that's 90 permute 25, and then all of that divided by 90 raised to the 25th. So 1 minus that number ends up being about 0.975, which is surprising to a lot of people. I mean, that is almost certain. A lot of people think intuitively that the answer wouldn't be quite as high. Imagine 25 students and you've got 90 numbers to write down. It seems like it could happen pretty often that everyone writes down a different number. But what we see is that actually it happens very seldomly. Almost always there will be some repeat. All right, so this finishes up our first section, 6.1, where we talked about the basic ideas. So it's really important getting this sample space of equally likely outcomes, and then understanding that an event is just a subset of the sample space. The probability of an event is the number of elements in the event divided by the number of elements in the sample space. And then the second thing is this complement trick. It's often very useful in finding probabilities if I can figure out what the probability of the complementary event is, because sometimes that's easier to figure out. All right, this is a good place to stop.